Test one. Test test. Is this one live? Test test. Test test test. Test test. I'm waiting for the
Check, 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 check. Check, 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 check. That's very strange. Why would that be a thing? Check, 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 check.
wireless mic. Now we're having some sound system problems.
Everything's working. Sarah wasn't communicating.
Test test test. Test test test.
Check, check, check. But everything will be applied.
All right, so I need to get.
I'm sorry.
All right, sweet. Oh man, they got the wrong guy to do this. How are you? Good morning, brother.
Supposed to be wearing a three-piece suit, man. This is good.
Like black hat? You like you got the black hat mode going on. Yeah.
This should be fun, man. How are you?
Good, good. How are you?
Dakota is missing today.
I'm good.
I told them that we can spot it a mile out.
Yeah. Well, I'm gonna get coffee before I have to go on in a few. What?
I don't ever see it.
Hey.
How are you?
I'm good, man. How are you?
Great.
What's up? How's life?
Great. Always.
Yeah. Yeah. Oh no, you're good. Hey,
Good to see you.
how are you?
Glad you were and you're speaking today, right?
I'm pitch hitting. Yeah. We'll see how it goes. Yeah. Yeah.
Got to follow up with that today. And then Chris was supposed to follow up with me. He's going to follow the radar. So I wanted to get to come out and see the towel.
Oh yeah. Oh, thank you. Pinch hitting. We'll see how it goes. I think it's going to be a lot of fun. hmm
Colonel doing all right?
He is. He is doing fine. Yeah, but he tested positive for COVID yesterday. So it.
It's still around.
Yeah, it's still around. He was in Fort Huachuca last week, so I'm sure there was a big meeting there. So I'm sure it all
Let's just blame it on
happened.
trade-off then.
Yeah, definitely. Hey,
Ready?
what's up? Yeah, why not?
Hands a little sweaty.
Yeah.
Just remember, you're the smartest guy in the room, right? I like your shirt. I approve.
I'm such a knucklehead.
It's AI, man. You gotta bid the latest.
Hey, what's up? Yeah, I'm pinch hitting.
Do you watch Westworld?
I do.
It's not on anymore. Westworld.
Westworld. hmm I was here last year. Yeah, was last year the first year? Which part of NVIDIA? California part, or you're on this side? Yeah, I'm on. Third. Public sector.
if Is this sounds okay? I'm John Stressing. I'm the Army for NVIDIA. I'm the AI guy. If you ever have any artificial intelligence related questions, by all means, please feel free to pick up the phone and call me. When Joe and I started planning these things a couple years ago, we were like, how can we make the industry event that we possibly can, And so I looked to NVIDIA's GTC as a model. Let's make something developers, artificial intelligence and machine learning companies to come in and give demonstrations, no pens and gimmicks and mark talking to technologists. And hopefully you're able to attend NVIDIA's GTCs, and hopefully this event today is a commitment to you to not just be marketing gimmicks, but to actually bring technological solutions to you. So by being able to offer CPEs, and the companies that we have across the street, are all ML ops companies. Hopefully this event's you learn. Hopefully everybody knowing more about artificial intelligence and machine learning than when they walked in. That's it.
John. Part of what we like to do with these events is give back to the community. So at this point, I want to call up from STEM Scholarship Fund. And scholarship award is Susan Shapiro, our HPE VP of Public Sector. And also from AFCEA, we have Claudia DiCarlo.
Okay. Guys. All right. Good morning, everybody. As Joe mentioned, my name is Lauren B. Ward. I'm the Executive Vice President for the FCA. Here today on behalf of our President, Arnold, who has the very difficult task of being on work travel in Hawaii right now. And also by Claudia DiCarlo, who sits on the Executive Committee as our Assistant VP for Small Business. So thank you so much for allowing us to speak a few moments. And thank you to HPE for generous donation. Many of you are likely aware of the amazing events that FCEA does in the community, including golf tournaments, happy hours, luncheons that are dedicated to enhancing collaboration between government and industry. But that's not our primary reason. Main mission as a 501c3, educational initiatives in the local community, mostly in the STEM fields. And how do we do this? We do this by giving back scholarships to both high school seniors and community college transfer students who are seeking higher education in STEM. In fact, shameless plug, our 2023 applications are open right now, so if you know any students who could benefit, send them to our website. We also provide grants and science teacher toolkits to local educators so that they can outfit their classrooms with the latest and greatest equipment to provide science education. And we also give back to the Boys and Girls Club of Harford and Cecil County so that they can provide after-school programming in STEM fields, as well as mobile STEM lab opportunities for their kids. We've created brand new scholarships at Harford Community College in both cybersecurity, and in February 2023, we also stood up a new scholarship for bioproduction, which we're very proud of. And in 2022, we gave back more than $60,000 worth of scholarships, grants, and donations to STEM education. So this wouldn't be possible without you. These are all funded by our chapter sponsorships, our event proceeds, and generous donations like the one we're receiving today. So thank you for making education a priority. You're really helping to inspire the next generation of brilliant young minds. And who knows, I mean, in another year or 5 years, they'll be sitting right next to you as your colleagues and the future change makers in the field of AI and ML. So thank you so much from all of us.
Thank you. Okay, now I'd like to introduce Susan Shapiro, who is HPE's Vice President of Public Sector.
Good morning and welcome, everyone. Mentioned the honor of leading our U.S. public sector business for the company, and I'm probably even prouder that I have a young son who is a lieutenant in the Army, who's a missile air defender based over in Okinawa, Japan. And as the Chinese continue to misbehave, you know, he's a very busy boy right now. So the most important thing that I have to do today, besides saying welcome and thanks for all of you to be here, is actually to introduce Bharat Patel, who has, you know, honored us with kicking our program off this morning. And, you know, Joe already mentioned that he is the product lead. Career in the Navy, and we've decided we're not going to hold that against him. And then after that, he moved to be a lead engineer for a number of years within MITRE. And he is really the first person who initiated for the Army research on machine learning. So, you know, without any further ado, I say, Bharat, why don't you come up, program for us.
Good morning. Can you hear me? No, I'm not on. Check. Closer, closer. Good. So I get a call last night on my way to a Viking convention, and then I had to turn around and head back to support this session with everyone here. Nobody laughed at the Viking convention. My braids. Come on, are you not alive? Do you not feel good this morning? Not enough coffee? All right. So the second part is I am super nervous. I think I need a clicker for everyone in here because it's always bad to give me a mic and an open floor to discuss whatever I want to discuss, and that's what's going to happen. So we have slides. Coming. So my goal is to introduce you some of the initiatives that are happening across the G2, Army G2, as well as PEO, Intelligence, Electronic Warfare, and Sensors, and then really talk about how we're leading the way for machine learning for the Army. So I won't spend too much time on this chart, but essentially this chart is Lieutenant General Potter's placemat chart, kind of how she introduces modernization efforts across her portfolio. You know, pivot towards modernization, pivot towards MDO, years in the making now. The bottom line for this chart is there are a ton of new sensor modalities coming online from across the layers, from the space, aerial, terrestrial layers, and it's all coming to PM, Intelligence, Electronic Warfare, and Sensors to support processing in a real-time fashion and being able to enable that through machine learning capabilities. What does that mean for everyone in here? Everyone in here is going to be part of the process that will enable that, right? So how many industry partners do we have here? Raise hands. Don't be shy. Higher. There you go, right? How many of you heard of Project Linchpin? I think we're doing our job, right? How many government folks are in here? How many of you are working on either machine learning related activities or AI? Right? What is your number one challenge? Data. Data. And I guarantee you, you've heard this before. We don't have a data problem, right? We don't have a data problem. There's so much data out there. I'm going to bring more. We are bringing even more data, right? Next 5 years, we're going to have direct access to certain space constellations. We're going to have networked access to space constellations. We are going to have new aerial sensors. So anyone heard of Hades? Right? So you're going to have new SIGINT long-range capabilities, radar, SIGINT, SAR, synthetic aperture radar. Anybody hear of TLS? That's the next generation ground EW. So we're going to have tremendous amount of data there. Anybody heard of, CPCE, Intel apps, tremendous data mesh, data fabric? Data is going to be everywhere. And what do you need to build machine learning? Data, right? Curated data, right? And every single one of you, I guarantee you, are chasing the same thing, data. And that is what Project Linchpin is going to provide to this community. We're going to be responsible for cleaning, curating data. We're going to be responsible for providing an ecosystem for model trainers to come into our environment and train against that data. Why is that important to us? Because the government wants to manage its own data. Right? All right, so I'm going to spend a little bit more time on Project Linchpin on the next chart, but one of our cornerstone projects, programs within the portfolio, Titan. How many people have heard of Titan? Right, I won't bore you to details, but the program's going excellent. That is one of our next generation ground stations that's going to be able to collect a ton of data. We are working through competitive prototyping now. We'll be up-selecting to one preferred partner later this year, and then we're going to go into another period of rapid prototyping with that preferred partner. In doing so, we're going to start introducing more and more technologies within that architecture. Why is that important? Because Titan's going to be one of our first use cases for Project Linchpin. Project Linchpin is going to be supporting the sensor modalities that are coming inside of a Titan. So what is that? I mentioned some of them, right? So you're going to have space-based EO, IR. You're going to have space-based SAR. You're going to have space-based ELINT. And it's also going to have connections to your aerial layer, right? And I mentioned Hades. There are other aerial platforms out there and sensor modalities that'll be coming into it. And then it's going to have access to EW and other data sources, right? But if you take a look at the manning, the proposed manning is focused on the current analyst workflow, right? So we are trying not to impact their current workflow. We're not turning those soldiers into data scientists. We are going to provide capability into that platform so their jobs are much easier in terms of being able to process all that information and making sense of that data that they're receiving. All right, my favorite chart. So Project Linchpin. Probably one of the fastest programs ever initiated by the Army. From idea to program initiation. Idea started in August of last year. Program was initiated in November of last year. There's a lot of questions still to be discussed and identified and worked through. We're going through all that. The next chart will kind of walk you through some of the timelines that we've already conducted. So we've already released 2 RFIs. We're aggressively trying to identify that ecosystem of partners that are going to come together to bring us a collaborative but yet competitive environment within Project Linchpin. So the way I like to kind of brief this chart, day in the life of Project Lynchpin. PEO IEWNS is going to be the first AI-enabled PEO. Why do I say that? We have an organizational structure that's happening within the PEO. We're going to stand up an O5 product office that's going to be responsible to provide AI, not only the pipeline as a service, but AI, in addition to AI as a service to the various products within the portfolio. Now, I mentioned we're going to start with Titan, but then it's going to expand to other programs within the portfolio. Day in the life of Project Lynchpin, understanding their customer requirements. Right now, their customers are the various sensor modernization programs within PEO IEWNS. First step is, what do they need to accomplish? So they work with their customers, they work with their user base, understand what their needs are. Step one, is it a software problem or is it a real machine learning problem? Once we determine that is, because software has come a long way. There's a ton you could do with software and software analytics, but machine learning is another level of complexity, right? So if it is a machine learning problem, our goal is to connect them with not only commercial providers, but GOTS model developers, and bring them into our environment. And what we are going to be responsible for, Project Lynchpin, is going to start doing the boring side of AI. I always call it boring side of AI. Get data, clean data, curate data, label data, and make that data available through a very competitive process inside our model training environment. And now you have V&V, right? So we need to start thinking about more than just F1 scores, more than just performance. We need to start thinking about Trojans, data poisoning, adversarial AI. Those are all concepts that we're bringing into Project Lynchpin. So responsible AI, no doubt, we're looking at that. We released our second RFI. It was based on tenets of TOR, traceability, observability, and replaceability. Traceability starts looking really at all the external activities that are happening from when the model was actually created. So there's a ton of concern out there that leveraging open source models creates some vulnerabilities. We want to be able to start managing those vulnerabilities. We want to start understanding how that model that was built mostly on open source, like we all know it, right? We all know there's some kind of YOLO or some kind of open source model that's been tweaked. We want to understand how that model was generated, who touched that model, what hardware, software was used to create that model, what fourth-party data labeling organization was labeling that data. So all concepts, right? But now, the observability part. Observability really pertains to what's happening inside these boxes. In order to support our modular open system architecture, observability and replaceability are going to be super important. So observability, we want to understand what's happening with our data as it's being transformed in some of these boxes. Why? Because it's going to help us implement better ability to plug and play and replace products if we understand what's happening with our data. And then we have replaceability, right? Replaceability essentially is going to help us focus on that plug and play architecture in between the APIs that we're defining. Because I'm going to tell you, here's a very contradictory thing I'm going to say. I don't want proprietary data. I don't want a proprietary solution, but I want to maximize costs, right? Isn't that wild? I just said I don't want proprietary, but I want to maximize commercial items. And the only way for me to do that is Tor, right? I need to understand what's happening in these boxes, and I need to be able to better define the APIs, inputs and outputs, and make them automated so I can plug and play. Very complex, right? So kind of day in life, that's our goal. Acquisition objective, right? We want to create, we know, just based on all the market research that we've done so far, there are hundreds of you out there. Every one of you have an opportunity to participate in this process, and we want to do that. We want to create this ecosystem of partners and then always be in an approach of best of breed. We don't want to be locked into a solution longer than we have to. We also want to start meeting some of the unders objectives for integrating small businesses into the process. So we're going to be looking for where we can incentivize small businesses or partnerships with traditionals and larger businesses to integrate into this process. So here's the challenging part, right? So once we develop these models and we get them integrated into a platform, how do we start receiving that feedback, right? We've seen a ton of manual. We've seen a lot of good things over Project Maven. We've seen a lot of good things happening with 18th Airborne Corps. One of the challenges is how do we bring that feedback into the system in an automated way to support the feedback loop, right? Because once the model is trained, it changes immediately when it's in that operational environment. So we need to start capturing those kind of metrics and bringing them back into the pipeline to support the retraining process. What this also allows us to do is start separating software from AI. What does that mean? Right? Now, my software does not have to have baked in AI, but through containerization and other approaches, I could have third-party model developers start integrating into software. What did I just do? I created another layer of competition suited for AI companies into my sensor modernization programs, right? So now I have another layer of companies that are actively competing in Titan, TLS, MDSS, and all the other programs. All right, let's see. I'm going to jump. All right. Project Linchpin focus. Our goal definitely is to establish a secure environment so we could do this. We want to be able to bring in our data and environment. We want to be able to maximize all the investments. So, right, the Army, does the Army usually lead the way in things from an AI perspective? There are DoD, IC, they've been doing this for a while. So we want to be able to maximize some of the investments that have been made there. We also want to make sure that, as I mentioned, we want to integrate small businesses as part of the process. But we know that we can't do this without some of the large companies bringing it all together. So that's going to create our ecosystem of partners to get this done. I haven't talked about the partnerships yet. So the partnerships that we've made across the path, CDAO. How many people have started working with CDAO or know their role in life? Few. So CDAO, Chief Data and AI Office, Mr. Honorable, Mr. Craig Martell. Several organizations have folded into CDAO, including the JAIC, Defense Digital Services, and other DoD-level organizations. Project Linchpin is going to be the first Pathfinder effort for them. They're going to look at Project Linchpin as how they provide support to all of the other services. So we're there on a weekly basis talking to Mr. Joe Larson and team to figure out how we are going to partner and pathfind together. Our Army S&T community. We have C5 ISR, we have AI2C, and we have Army Research Lab, all part of Project Lynchpin's team. I mention this because we are not only trying to centralize a capability, but we are trying to centralize some of the talent. AI talent is not just vastly available, right? It's not like software and software developers, especially on the government side. So we are trying to centralize the talent as well within the program. So they're absolutely key players in this whole thing. All right, and here's some timelines for you. So again, bottom line, the Army wants us to move fast. The Army wants us to establish a secure, trusted environment so we can deliver capabilities to our programs. We want to stop paying for the same model multiple times, right? We want to optimize those models. We want to make sure that we partner with industry because you guys have the talent. We have the oversight, you have the talent. But we can't do this without you guys. A ton of industry outreach, because we want you guys to understand what our requirements are. And as things evolve with our strategy, we want to put that out there. So then you could have enough lead time to create any partnerships, to create any products or questions that you may have. And we have a continuous open door policy. I think I've met, how many people have I met with? I am not doing my job then. Well, unless everyone's just tired. But I need to start meeting with you guys more often then, right? I have an open door policy. There are members of the Project Lynchpin team here. Raise your hand, please. Right? So any one of those hands, if I'm not available to talk, any one of those hands, please feel free to touch, reach out to, and talk today. And then Mr. Jess Stock, Chief Engineer for ISNA, he's also here. He will answer questions as well. I'm going to pause there to see if any questions from the group. Yeah. Can we handle that load? So first one, we had over 70 responses. It took us a few weeks. Are you guys all going to use ChatGPT? Is that what you guys are doing? Yeah? Is there anything, in theory, anything wrong with that from just a response perspective? Would it be wrong for me to use the same technology to evaluate and summarize? Right? So we're looking into that. I don't have a perfect answer for you, but right now we are case by case. We're looking at everything as we go through this. Yeah, Adazaz, thank you for that. So would it be for the first AI-enabled program, would it be impossible for us to think about that already? Right? Are we looking into that? Okay. We are looking at everything. We're looking for ways to improve efficiencies across the board, not only for our warfighter, but for our own sanity. So I'm not going to answer that specifically. Right? Next question. There's got to be a couple more, please. Yes, Gary. For, if I have to, Gary, if I have to. No, okay, so the idea was born out of PM Intelligence Systems and Analytics, right? So within our portfolio, we own Titan. We are going to use Titan as a use case for us to figure out our governance, TTPs, ConOps, and how we are going to support other programs outside of PEO. So that is why we are focusing on Titan, because we own it within our portfolio. It also has literally all the sensor modalities that are going to be needed to be part of a sensor AI pipeline.
Okay, so I see all the layers for MDO right there. That's going to be feeding your Titan systems. How is Lynchpin again going to support it? I mean, maybe you just answered it. I just want to double check, make sure I got it. So you
Going,
all the MDO stuff, but where does Lynchpin? How does it?
going back to Project Lynchpin, what is it? It is a machine learning environment that trains models that are based on those sensor modalities and provides a model to programs to support their needs. Go ahead. Next. Do we get that question a lot? Does industry ask us that question? All right. So what is the difference between Project Maven? So Project Maven, good or bad? It was the first DoD AI Pathfinder with the objective to introduce and accelerate AI adoption across their services. Did they do their job? I think they've provided us a ton of lessons learned on how to actually integrate non-traditional small companies into a process. From that perspective, we're carrying those lessons learned into how we are going to be kind of working with industry. Where we are different, obviously, if you guys don't know the history, so Project Maven has officially ended. The Pathfinder efforts ended its transition to various components within either the IC or different organizations. Where we're different, we are not providing an end-to-end solution. So Maven provided a Maven Smart System that did AI-enabled mission command. We are not doing any of that. We are working with our program offices. Our goal is to really provide them a capability that integrates into their programs, right? So we are not providing an end-to-end capability. And there's definitely some other areas that we are different, but those are some of the big ones. Yes, so Ms. Swanson, team, working, data mesh, data fabric. We are collaborating, we're working together. So data mesh, data fabric really starts to get after that early part of cleaning your data or providing your data in a way that can be consumable. Across the battle space, it's going to support analytics and the ability to be more interoperable across the force. We are working with them. There's another layer of complexity when it comes to machine learning. Although data mesh supports the concept, we also need to do another layer of cleaning, curating of data to really support the 10 or 15% of data that's really important for machine learning, right? So with the mesh, data is everywhere, data is accessible, but that doesn't necessarily help my 10 to 15% of data that I really need in order to support the machine learning process. So long story short, or short story short, we are working with them because it's going to be important to get that data into our pipeline. There's so many.
Quick
Good.
question. Can you make a comment on how Linchpin is linked into JADC2? And will it ever go across branches of service? Comment on that?
Okay, so I'll give you an example. So Titan is the link in this scenario. So Titan is the link to JADC2, right? It is the Army's contribution to JADC2. We are providing enabling models into a Titan or into another program to support their capabilities. So indirectly, we are supporting JADC2, but there's no direct link. We are, from a JADC2 perspective, right? Remember what I said, number one problem is data. We are working across the DoD and other services to determine what our machine learning data strategy is. So Air Force has data, Navy has data. How do we combine our data either through a centralized location or through a mesh so we are all sharing data, and then now it's all cleaned, curated, and labeled in the same way in order for us to build models effectively. One more? Okay. And then I'm here so we could go. I talk to you all the time, Bill. Stop. I think I'm getting pulled.
We do want to stay on schedule here. But Bharat, that was fantastic. Thank you. Jessica promised me that you guys will stick around, so lots of opportunities to talk to the linchpin folks.
box and continues to hit the same wall. So literally, we would start that running at 6 o'clock at night. The next morning, because it would run all night long, you'd come back and you'd end up with a model, which literally was a vector, a matrix, that would allow you to very quickly query shortest path between A and B, shortest path from C to Z, right? The algorithm was that thing that I could now take and drop into any square, any grid size, and let it run overnight. And the next day, I'm going to get a matrix that would allow me to identify all my points down one side and the fastest way to the other point. Does that make sense? Right? Algorithm versus model. Model is what you then take to the field. Algorithm is what takes so much churning depending upon how big your data set is. Algorithm is all those iterations. Running that algorithm over and over and over again on refined data is the chore, and that's where you usually get GPUs involved. So apologize for these slides. These slides will be better looking when they send them to you, okay? Slide, please. So what about deep learning? Deep learning is really where you kind of start working your way down a stack of decisions, right? Like a neural network, almost like ensemble learning. Ensemble learning is where you start refining, you know, this is an animal, this is a four-legged animal, this is a cat, this is a Siamese cat, right? Working your way down from a recognition perspective. But this is typically where we see deep learning algorithms running. Natural language processing. These are very intense computational efforts for deep learning. So we talk big artificial intelligence, where just a computer can mimic human behavior. Machine learning, where it trains itself based on an algorithm. It didn't know the 10 by 10 grid with the letters A through D and how to get from one to the other when I went to bed at night, woke up the next day, and it could tell me all that. It trained itself. And this is where we see deep learning coming into play. Okay, slide, please. So that's kind of your primer on AI/ML with the language that's going to be important as you have these discussions. And, you know, it's always dangerous to come up second when you're doing the academic side, because what if I said something 100% opposite of what was just said? But no, everything that was just talked about with Project Limson, with PEI, EWNS, they're using the language correctly. They're talking about it the same way. The challenge is a lot of folks don't understand the language when it's said to them this way. So that was the intent that Ask Joe had, was to kind of have an academic primer set, so that the rest of the day we can talk about things and have the basic understanding. So now I was asked to talk about what we're seeing in the space for organizations that are starting to adopt machine learning and artificial intelligence. So when I say organizations, you know, I'm the public sector CTO. Susan runs the public sector for HPE. But this is true no matter what your organization is, whether you're Home Depot or Walmart or Disney, where you want to enable an environment where you can have algorithms running. You heard it just said the number one thing is data, access to data. So what you're going to see, a lot of what I'm going to talk about is how you are getting access to data, how you're setting up access to data, and how you're authorizing systems and services to run on your enterprise. Slide, please. So, you know, I made this Army-esque, okay, with the edge being the operational edge and the center being your Army Enterprise Private Clouds, formerly known as your AEDCs. And then you got your Sea Army hyperscaler environment. But again, that could be Home Depot stores, this could be their primary data centers, and this could be their hyperscaler environment with Azure and AWS. Doesn't matter, okay, it doesn't matter. This kind of an edge to core data center to hyperscaler environment is the evolution of the enterprise today, right? The hybrid enterprise is able to run workloads where they make sense, because the trend right now is that data is getting too big to move. What you just heard talking about with Project Titan, we are talking hundreds of gigabits of data coming down to those tactical nodes, right? Most folks in this room are understanding that 10 megabits per second is a big deal at a forward headquarters, right? You don't get 10 megabits per second unless you got a couple of decision makers on the ground with you. That's high bandwidth, 10 megabits per second. Once in a while, you're going to get one of those SES birds overhead, and you'll get a couple hundred megabits per second. But when you're bringing down hundreds of gigabits per second, like Titan's going to be, you need to be making the decisions and the inferencing stuff there, right? Data's getting too big to move in the military. It's too big to move in Walmart and Home Depot and everybody else too. It's all video. It's all other things like that. Slide, please. So when we start talking about, one of the first things we got to worry about is we have got to get that, understand where our data is, We got to presume, or we got to make sure the data is usable, it's clean, there's a pedigree to it, because we talked about observability during the last session. We stayed away from, in the private sector, we talk all the time about trustability. How do we trust AI? How do I trust that decision that's being suggested to me as the human? And it comes back to, you better trust your data. Your data has to have provenance. You need to know where it comes from. You need to know it hasn't been changed. Okay, so data is the key. And what's happening in the world of the enterprise is you have data out at the edge, which is too big to move. You have data sitting in your core data center. And then you may have data that's long archived sitting somewhere in a hyperscaler environment. All of that has to be brought to bear against an algorithm to train a model, depending upon what you're trying to do. Slide, please. So the propensity today is for enterprises to put really powerful computing out at their edge locations to deal with the amount of data coming in. The right answer today is the workload, a lot of them being cloud native, is moving to the data. The workload is going out to run where the data is, because you can certainly send a 10 megabyte container image to a data center or a high-powered edge computing where you've got gigabytes of data. A lot easier to send a small workload out there, get your insights, and send your insights back. So organizations, whether, again, that be your Home Depot or otherwise, they are pushing edge computing out to the max. Your Dick's Sporting Goods, your auction houses, your casinos, the data is being processed on site, because moving data has a couple of implications. One, you got to prove that what you sent is what you received. You immediately have an integrity question when you move data, right? How do you know it arrived the way it left? On purpose or accidentally, depending upon your adversary. There's a green carbon cost to moving data, right? I mean, you're moving gigabytes of data through switches, and that all takes electricity, and there's fiber. And for companies today that we deal with in the private sector, there's a carbon footprint requirement that you got to answer the mail when you're moving terabytes of data that they'd rather not pay, because everyone's moving towards a carbon zero, right? That's what we're all going after. So data is predominantly staying put in the private sector. Why that benefits us in the DoD public sector side is because we can't move the data. So we have to deal with it where it is. So the commercial world is not moving their data for other reasons, but for us, we don't have a choice. With gigabytes of data being collected at the forward edge, you have to process it out there because you can't bring it back. So you're moving compute out there, and that compute's got to have graphical processing units, GPUs, accelerators. In some certain situations, if you know exactly what you're going after, you can put a FPGA out there, a field programmable gate array. Reality, though, is GPUs, general purpose graphical processing units, which allow you to do that algorithm training in parallel. Okay, that's the concept behind GPUs, is parallel processing. Instead of running one algorithm at a time on a data set, you can do multiple algorithms on multiple data pieces at the same time, dramatically accelerating your learning. So you're putting GPUs and high-performance computing out there. Slide, please. And then in your core data centers, you're seeing people move to HPC, high-performance computing. And when I say HPC, that means these are systems that are very much set on very big I/O coming in and out the back, hundreds of gigabits in and out the back. And the trend has become moving to more GPUs than CPUs. I mean, there was a day not very long ago when it was all about CPUs, putting 32 sockets in a single system. We are now unleashing, and all the OEMs are moving in this direction. The next system we're putting out is 2 CPU sockets with 4 GPUs, right? That is an inverted ratio. It used to be equal, or it used to be more CPUs, and now what's being demanded by the private sector is more GPU, more PCIe slots, and sockets, okay? 2 CPU sockets, 4 GPU NVIDIA A100s because of the parallel processing machine learning for HPC in the core. And of course, in your hyperscalers, you have access to HPC as well. Slide, please. Okay, so you got to get compute. You heard it mentioned talking about data fabric, okay? So the next thing, enterprises who want to take advantage of machine learning to break down those silos of data is they're installing a data fabric or data mesh. Now, what this data fabric does, by and large, is it brings all your data up to visibility, right? One of the primary things that a data fabric does is it provides you a global namespace. And what that means when I say global namespace, right now, historically, in the DoD and the Army, I retired out of the Army in 2011. And you heard Joe say I was the CTO at SOCOM from 2011 to 2018. The challenge we have is data is everywhere and it's siloed. And when I say siloed, I mean he's got a ton of data I want, but I don't have a username and password, or my CAC card doesn't get me access to his data. How do I get that data? Right? How do I even know he has it? We had an interesting discussion not long ago where all this money flowing out of the White House for AI and machine learning a few years ago, and Johns Hopkins wanted to do a longitudinal study across Vietnam vets, Agent Orange lung x-rays across 165 VA hospitals. These are gigabyte images, and you know, some of these VA hospitals, unfortunately, are connected at dial-up speeds, right? I mean, how is Johns Hopkins going to get access to all these images scattered all over the U.S.? They don't even know they're there, right? And this is privacy data. So a data fabric brings that data up. The global namespace will bring up the name and the metadata to say, hey, maybe he doesn't solve the access problem, but it'll come back and say, hey, Frank's got this data, and this is what he's got. So at least now the data fabric lets you know it exists. And then whether Frank likes you or not will determine whether you get access to it, right? So the data fabric is critical. It breaks down silos. It handles your encryption. It handles your replication. It's intelligent in that it will move data for you based upon your rule set. Okay, there are a lot of folks out there. I'm not pitching a product. There's a lot of data options out there, but just understand the role this plays and why you just heard IEWS talk about data fabric. Because we have silos, we're going to collect it at the edge. We have all this data sitting at the edge. You know we can't send it back, but if I tell you it's there, you can send a workload to my high-powered machine with a GPU, let me run on it, learn from it, and then send it back, but you got to know it's there. Hence the intelligent data fabric requirement, okay? So data fabric's key to getting access to your data. Slide, please. Then you got to have an intelligent software-defined wide area network. So this is SD-WAN. Again, you know, buzzwords. Everyone's talking about SD-WAN. The purpose of SD-WAN is virtualizing your connection and your network. The reality is, yes, you got to have exquisite hardware, right? HPE, we all make exquisite hardware. But when you start wanting to look at multiple path analysis, ensuring data delivery, ensuring that your connection is there, a software-defined wide area network does that for you, right? So on the ground at a JTF headquarters, we're going to have satellite out. We're going to try and get fiber. We're going to try and get, worst case scenario, we got HF, right? The PRC 137 kicking it 64 kilobits. God bless us, right? Point is, hey, it's something, right? You need something. And your SD-WAN is going to do that optimum path analysis for you at the same time encrypting, at the same time protecting. So you've got your data fabric elevating everything, but then giving you that access is going to be your software-defined WAN is going to help you with that, okay? Slide, please. So let's talk about multi-cloud identity, okay? We don't talk about identity very much. You know, so throw a chair at me if I say zero trust too many times. The reality is zero trust, or whatever you want to call it today, is 100% based upon identity and attestation, right? It's about whether I trust you or not and how you are going to convince me to trust you. How are you going to attest to who you are? Now, what we're facing in the private sector is this is hard in a multi-cloud environment. Go back to that first picture where you got all these edges out there, and we've got 3 or 4 different, maybe they're coalition countries, right? They don't trust each other at the edge. Maybe it is different enclaves from the 10th Mountain Division, 82nd Airborne Division, right? They're all their own enterprises. You got to have a login and password, or your CAC card's got to be recognized by 82nd to log into 82nd's environment. But I'm with the 10th Mountain Division. So how do you get this information? And what we're facing in the private sector world is, hey, look, our hyperscalers didn't make a living by making it easy for one hyperscaler to reach into another hyperscaler from an identity perspective. There's no value in that. I'm not even going to name any of them, get them all upset with me because, hey, any hyperscalers in the room? Love you. But hyperscaler A doesn't make it easy for a workload running in hyperscaler B to burrow in and take data or even look at data. They use different identity engines. And so in the private sector, as we walk in and we say, hey, the healthiest way for your enterprise to be set up is multi-cloud. You ought to take your enterprise, tie it into at least AWS and Azure and Google, and you should be connected so that you have burstability and play them against each other. And they're like, okay, great. But you're not multi-cloud if you don't have the ability for workloads to seamlessly move into those environments, or a workload riding on-prem or a workload sitting in AWS to reach into Google and get your data. Well, how do you do that? Automatically. So attestation of services is hard. So this is how it's happening in the private sector. Slide, please. This is an open source project at the Cloud Native Computing Foundation, Spiffy Inspire, okay? Spiffy Inspire, Google it, you can bring it down and start using it. There are probably a dozen Fortune 50 companies today running Spiffy Inspire as their multi-cloud attestation identity for services. Okay, very easy to use. Basically, without getting into the code of it, the code's online, go get it, try it. Basically, what happens is Spire is your runtime engine. Without belaboring the point, you end up running a Spire engine in each of your environments, AWS, Azure, Google, on-premise. And that Spire engine is what's trusted in that environment. And then you trust your different Spires to each other. So you basically have a transitive trust through your Spire engine, okay? Now, the way Spiffy works, you're not using shared secrets anymore, so your shared secrets can't be taken. It is a very, 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 very short certificate cycle where even if something happened, the certificate is not worth anything milliseconds after it's requested. It is fascinating how it works. And again, this came out of incubation last June. It's been the CNCF for years. And this is moving into production for many, many folks. We're incorporating this into our data fabric. Because otherwise, you don't have any way of going multi-cloud data. This is attesting to services. Applications are requesting their own. Slide, please. And this is an example. If you're familiar with Cloud Native at all, if you're familiar with the Service Mesh Istio, when you have requests running around in a Kubernetes Cloud Native environment, your Istio Service Mesh is actually getting the certificate for the TLS connection from your local Microsoft Certificate Authority. Locking your Istio into your enterprise, because your Microsoft CA doesn't mean anything to Google or AWS. Maybe it does to Azure Identity Service if you federate it with them. So the point is Istio even, when you try and go multi-cluster Kubernetes across multi-cloud, Istio, your service mesh, is locked in by your certificate authority. So this is a project we have running, and there's a couple other ones out there where we're actually replacing the third layer of Istio, which is called Citadel. And instead of getting your MTLS certificate from your certificate authority, you're getting it from a Spire engine, and you put Spire anywhere you want. And all of a sudden, now your Istio service mesh can go multi-cloud. So nobody wants to talk about identity and attestation because it's hard. We always pretend like it's going to happen. It's not. Workload sitting in the 82nd is not going to be able to reach into 18th core or into the 10th mountain. It's not going to happen because they're not allowed to cross those attestation boundaries. So in the private sector, right now, this open source project is how it's happened, Spiffy Inspire. Take a look at it, download it, give it a shot. It's pretty simple to turn on a Spire engine, and all of a sudden, you've got this trust framework where things can fly around multi-cloud. It's interesting. Slide, please. So that said, boom, you've got to have some sort of trust attestation, and in this situation, I'm representing Spiffy Inspire, cool little icons, that's going to allow your edge and your core and your hyperscaler data centers to all attest to service workloads. This is not going to replace your CAT card, right? I mean, humans are a little different, right? This is not a CAT card replacement. This is that replacement for the application, machine-to-machine services running around your enterprise that you're going to want your smart intelligent systems to move a workload down to run at the edge. Well, why in the world would the thing down at the edge let you come spawn a workload there? Why is it going to trust that workload, right? That's what Spiffy Inspire does. So here's your picture, right? From the neat little edge to core to hyperscaler environment, you need to have a data fabric. You need to have powerful computing with GPUs sitting out at the edge to do that retraining when required, to do the heavy ingest of live streaming data. In the main data center, you're going to have high-performance computing with massive GPUs to do parallel processing and build those models from your algorithms that you can then deploy out and make better sense, right? You got to have an intelligent SD-WAN, and you're going to need to have some way of attesting and identity and providing identity to your service workloads so you can truly start experiencing this span of control where your different little enterprises, all with their little own domain name services and their own little Active Directory certificate servers and all that stuff. That's great. You're never going to get away from that because your laptop needs a cert, so you're going to have a certificate authority with a domain controller for your 18th Airborne Corps. You're not getting away from that. But then you got to breach above that, and this is how it's happening in the private sector. Slide, please. All right, one more slide. I'm going to show you this too, because this is a Google thing you need to look at. When we start talking about working at the edge, this is what we've seen as the progression of doing machine learning, where we move from just happening at one spot. The problem with machine learning at the edge is it's called geographical bias, okay? If you run your models only at the edge, you're going to be geographically biased based on your edge. So, for example, if you're running your computer vision algorithms and you're doing classification in Africa and you start looking at cats, well, you're going to end up with a tiger, okay? If that's the only place you train your cat algorithm and build a model, anything that's furry and four-legged and pointy ears and a long tail is a tiger. Well, when you run that model in San Francisco, you're going to get a tiger, right? So geography matters where you're running these algorithms. And so I want to highlight that there is another open source project on GitHub for swarm learning, which basically allows your edges, no matter where they are, to share their insights and retrain on the fly, okay? Again, the code is all there, the user handbook's there, but swarm learning is enabling us to break that geographical bias and improve our ability to retrain algorithms to build better models. And there's a lot of examples on that website. Slide, please. There's a slide again. This is the GitHub website right here. Just look up swarm learning on GitHub, okay? Great, and it's very simple. There's a tutorial how to use it. But if you have an ML algorithm already, this isn't going to create an ML algorithm for you. If you don't have one, we got to start somewhere else. But if you have an ML algorithm that you are running now to do data insights, okay, go get the swarm learning, download it for free, and try and now create a swarm with multiple nodes and train it separately. You can set up in a lab, right? Have it do object detection of 4 different things, sitting on 4 different little PCs, and then share those insights. It is fascinating how this thing shares insights, and it's very simple, okay? So you can get after edge analytics and edge learning without having to bring everything back to a core data center and recompute it there using a swarm learning technique. Okay, that's my last slide, and I'm sorry for rushing. I've got 30 minutes. And I got to get off. So, yes, sir. Yep. Right. Yeah, so the question is about where you have an adversary intentionally trying to feed you bad information, right? And how do you handle that kind of ambiguity slash bad data? And it comes back to how you trust your data sources, to be honest with you, right? You heard it just talked about in the last conversation. You know, that has got to be an active effort. As much as we are looking at SPIFFE Inspire to attest to workloads, there's also got to be a way of trusting the data provenance, where it comes from, and the fact that it hasn't changed in route. So that all heads back to data collection techniques, right? When you collect your data, and we deal with some of this in the private sector when it has to do with law enforcement, I guess that's more public sector, but when you collect the data, how are you storing it in such a way that you can then prove its provenance, right? That it hasn't been spoofed, that it comes from one of your valid sources, right? So the way you meta tag it, the way you encrypt it, and the way you store it is the reason why you trust it. And I'm going to bring up one other thing kind of leading to that, where one of the challenges we have, and I'm talking now big data, okay? We don't say big data anymore. We used to say big data all the time, right? Now we don't say big data anymore. But big data means volume, velocity, and variety, right? You got to have all three to have a big data problem. But part of the challenge we have back to trusting AI is it's got to be repeatable, right? You got to be able to show it again. If I go run through all this stuff and then come up and go, hey, look, it says B. Like, well, why does it say to pick B? I don't know. I mean, it says B. Run it again. Well, if you run it again and it comes up and says C, now all of a sudden your confidence drops. What we have discovered in the world of big AI is data matters, but not just data, but data versioning matters, and the order in which you feed the data matters. So you have a huge growth in the private sector in companies that are getting after data management at the petabyte scale for feeding ML algorithms to train models, okay? Because for it to be a trustable AI model, you've got to be able to do it again and again and again. And then once you do that, now I add a bit of data and I run it again, and I can see the change. But if I can't run it 3 times in a row and get the same result, it can't be trusted. That means you've got to have a way of managing your data, versioning, ordering. There's a company out there called Pachyderm that does it, but that's becoming critical. In trustable AI, you've got to manage massive data sets and feed it into the algorithm in the exact same way for it to come out and be the same answer as the last time. If you just invert 2 data sources and send one before the other, Katie, bar the door. It's not going to be the same. And then everyone's rubbing their head and going, your algorithm's horrible. We can't trust it. You got to feed the data. And when you're talking about petabyte scale data, it is a challenge. So there's a whole growth industry about managing this data. And the Army needs to worry about it, because the Army's going to be dealing with big data sets. You can't just ingest the data willy-nilly any way you want. If you have a model and you want to build that model again with a little more data, you got to build it the same exact way up to the point where you're going to add new, or you're going to wreck it, okay? So again, Pachyderm is a company that does that. So, but a good question. Trusting data is critical. How you collect it, how you store it, how you give its provenance, trace it back to its source, it's all critical. So I'm getting the hook. We are 8 minutes over schedule. I appreciate your time. I'll be here all day. And I look forward to talking to you. But today we're going to talk about GPUs. We're going to have a lot more smart people come up and dive deeper into this. This was just kind of your primer about how your evolution of your environment will support AI. So thanks for your attention. Appreciate it.
Awesome. Thanks, Bill. So next speaker we have today, the seniors architect. I was talking to John. What is it? It happened to be around TC. All things EO, ELIN, all that stuff. So without further ado, Brent, take it away. All right, cool. Thank you, Brent. Hey, everybody. So I hope you can come up here and talk to Brent if you're interested in modern sensor processing. Brent will be here for the remainder of the day. So come on up and ask him all your hard questions. Then I also have Jen Lombardo here. She's the NVIDIA engineer for the whole Army. So, come up here and challenge her. They're both ex-MITRE as well. So very, very smart folks. All right, with that said, we're going to take a half-hour break. There's going to be some snacks, there's some refreshments. I hope that everybody here will stretch their legs, head across and look at some of these technology demos that we have from these partners. I asked them all, no sales pitches, just technology demos. So, hopefully you can go over there and see what the art of possible is. And then we'll come back in here in about a half hour. What do you think, Joe? And then we'll get things kicked off with Colonel Sai, right? Colonel Sai, yeah, right. Okay. So, thanks, Brent.
All right. Exactly right. I mean, it's been what, 20-something years? You learn to listen to a word I say. All right, great.
You guys hear this? There we go. That's better.
I can see it right there. Okay, thank you.
Start our presentation here. I want to introduce Joe Zerilli. Joe is the Vice President of AI for Parsons. He's been working in this AI area for over 30 years, which I bet there's nobody in this room that can say that. He's a wealth of knowledge, particularly in applying AI to practical DoD uses like electronic warfare, wireless, SATCOM, and a variety of other military applications. He's got a Master of Science in computer and a double E from Rutgers, and he graduated from the Rochester Institute of Technology, which is a very good school, and he's published a whole lot of different papers in this area. I was particularly impressed with the fact that in 1997 he wrote a white paper on financial prediction using neural networks. So he goes way back in this area, and we're looking forward to hearing about his experiences and what he's working on. Thank you, Joe.
Thank you very much. Can everybody hear? Am I turned up? No. Hello? There you go. You can hear me now. All right. So what I want to talk to you today about is what's called a genetic algorithm. I think a lot of what you hear when people say AI is based primarily on neural networks. Everything you see in machine learning, object recognition, all those types of things, even ChatGPT, at the core is a neural network somewhere. And I think it's become a little too synonymous, AI with supervised machine learning. And so I want to maybe put a new tool in your toolbox called a genetic algorithm. What I'm going to do today is try to give you like a little bit of an overview, give you not quite a deep dive, but enough technical that you'll be able to go away and say, hey, I think I can apply this to areas that neural networks just don't make sense for. So something new. I could have talked about neural nets too, but I thought that would be So what is a genetic algorithm? When are they useful? How does it work? I'll give you a little idea of how it works and how it does what it does. And then, we'll go into a little bit of the design considerations, things that I think a lot of people shy away from using them because when you get down to the nitty-gritty, some of the things get a little tricky on how to implement in real-world situations. And then I'm going to show you some things we've done with genetic algorithms and also some other projects. Okay, so genetic algorithms are really one of a class of what's called evolutionary algorithms. And evolutionary algorithms just mean that they start with some premise, they modify some parameters, and then they keep going until they find an acceptable solution. So they're iterative algorithms, kind of the way training a neural network is. You could actually use a genetic algorithm to train a neural network. It's not a very efficient way to do it, but you could do that. It's called a meta-heuristic because it's not exactly a closed-form heuristic algorithm. It's kind of a solution that provides a sufficiently good answer to a problem. And the reason, so you say, well, geez, why wouldn't I just use an algorithm that gives me the answer? Well, because there are some problems that are so big and so massive, or you have a solution that just takes too long to run on conventional hardware, even with GPUs and everything else. And I just need a good enough answer. And there's a lot of situations like that, and I'll show you some of those. So that's why you'd want to use this meta-heuristic. So what is it used for? It's really used for search and optimization problems. So I have a big search space. I have a lot of things that are possible, but I want to find the things that are important to me. So, and it does that by using what's called a merit function, which is really just defining your goals. What is important to you? So you define that one parameter, or not one parameter, but one function that represents what goodness is to you. And that's what drives all your solutions towards what you need them to be. So what I'm going to do is give you a little bit of an example that will kind of solidify it a little bit in your mind as to how you would apply something. Now, this is a pretty simple problem. It's called the traveling salesman problem, if you've ever heard of that. So you've got a UPS truck, and he's got a bunch of packages. And in this example, he's got to go to 4 different locations. Pretty simple. He wants to do that in the fastest time. Not use the least amount of fuel, but the fastest time. So you can use a genetic algorithm to solve this. Or you could use with just a brute force algorithm. And so what I did here is I show you the solution space. So there's every possible combination of going from the distribution facility to visit all the nodes and get back to the distribution facility. So if you look at all those, you'll see that there's n factorial different possible solutions to that. And so, there's 24 different paths. So 24 different paths. Well, you can, in this one here, I list them all out in a nice spreadsheet, total up the time that I got at travel time in New York City at 3:30 in the afternoon, how long it would take to get to each one of those locations, right? So now I can just sum them up. I can see really quickly that the best solution is DCBA, right? So you go to D first, you go all the way around, and that's the best one. So that's great. So why would I need a genetic algorithm? Well, if you have 50 different locations, now you're talking about 50 factorial. What's 50 factorial? That's a big number. That's 3 to the 64th power. So, even if it took you just a nanosecond to evaluate each route, it would still take you how many years? 9 years. 9 to the 47th power years. So now you can start to think about, this is a simple problem. Now, if you have a big problem, like I'm going to show you some of the other ones, they're basically unsolvable with a traditional algorithm. So you can use this to kind of get close. If you want to ask questions along the way, I'm up for it. Oh, did that work? There it goes. So how does it work? What it really does is it doesn't just have one solution that it's trying to optimize. It has many solutions, a population of solutions, which are really genomes in a civilization of people. I'll put it that way. So what it first does is it just takes a bunch of random solutions. So in this example I'm showing you here, I have 12 different solutions. And what I do is I run them through that merit function, and it gives me a value that says how good each one of those solutions are. And then what it does is it sorts them and says, okay, now I got my 12 solutions, and here's the rank. So now after that, what it does is it does what's called selection, and it looks like the fonts don't come out on this. But that's mating up there, not Maddie. And, oh, there's the NG on the bottom. So, so what it does now is it randomly selects 2 of those solutions and mates them together. And what it does is it then swaps that genome at selected random points and creates new offspring. So now you have all those new offsprings in the crossover stage where you swap values from the genome between each of those individuals. So now you got a whole bunch of new solutions. So now you take those solutions and you can then have, so this is an optional stage, but it's usually desirable to have a mutation stage. So now what you do is you go in and you modify some of those solutions just a little bit. You push them in one direction, push them in the other direction. You do all that randomly. Seems like a lot of work, right, to get there, but it really works well. And so now you have all these solutions, and now you rank them again, right? So now I said, okay, now I've got all these mutated solutions and everything over there. I rank them all again, and now I've got all these new ranks. So now what do? You take those, and now you replace them in the population. So the worst solutions die. They go away. The better solutions rise to the top. And then you say, I look at that best solution up there, and I say, is that solution good enough? You know, does that really solve my problem? And so that becomes a little tricky, because you either have to say, the algorithm's never going to get better, so stop because it hasn't improved, or you know what a good solution is. Maybe your merit function is such that you know if you get a value of 27, it's good. You know, it's good enough for what I need. So you can stop. If not, you go back, you redo all the crossovers, you re-rank them, and you just keep going until you've got an acceptable solution. How does that sound? Any questions about that? There's one. Oh, I got this one first. Sure. It really isn't based on graph theory. There's not a bunch of connections. I wouldn't say it's connections with weighted connections. No, that's really not what it's based on. Maybe the problem I showed you was kind of graph theory, but the algorithm itself is not. Because the graph theory, if you go do graph theory and try to traverse all those nodes, it's going to take you forever. You're never going to be able to do it in time. The solutions, the graphs are too big. You can't even store them locally. It's just going to be tremendous. What happens here is the genome, the population, if you do it smartly, it becomes just a bunch of values between 0 and 1. And so the strings can be very, very, very compact and small. You can store them, you know, on a desktop PC, and you can solve some pretty big problems just on a regular computer hardware. And you can use GPUs for the merit function to really speed things up, you know, so because those can be done in parallel, but the rest of the algorithm has to be done serially. Yes, I'm sorry, go ahead.
Have you compared your genetic algorithm approach with a quantum machine learning or a quantum game theory model?
I have not, no.
I mean, quantum theoretically is supposed to look at all of the possible, let's say, 100 factorial.
The problem's going to be most of the genomes to solve real problems are pretty long. They could be 500, 600, you know, genes. In quantum, you know, you're going to have a limit probably like, I don't know, you can do a simulation, but those simulations are going to be slow. And the quantum computers nowadays, you know, are expensive and 64 bits. Absolutely. Absolutely. Quantum would make this useless. Absolutely. But it's just not practical right now. I mean, unless you know it is. You got one in your basement. that I know of. I mean, you know, I haven't worked with it. That's the first time I got a quantum question. Okay, so when you're doing these things and you're putting your thing together, you're trying to solve a problem. The first thing you have to do is you have to design your genome. You know, what is each of these values going to represent in my problem? It's real easy with the traveling salesman problem. It's just the string of which nodes do I go to in what order, right? That's simple to understand. But some of the other problems may be a lot more complicated, and we can go into those if I have time. But one of the first things you need to know is you got to be able, when you're doing all those crossovers and mutations and things like that, you want to end up with genomes that represent valid solutions. A lot of times what can happen, like in that example there, you end up with 2 4s. So you don't want 2 4s. You don't want to go to the same location twice. So you got to make sure your algorithm for doing the crossover and mutation are such that it doesn't do that, because then you end up wasting a lot of time. You can assign a really high value in your merit function to those things, but that slows things down. So that's a good thing to know for a beginner. Then the other thing is you have to, the merit function is really the heart of the algorithm. It's going to drive everything. It's going to say, you know, it's going to evaluate every solution and what it does. Here I put a simple merit function for, you know, just adding up all the times for each of the stops and getting a value for the estimate time of arrival for a solution. But you're going to see that when you have you might have multiple objectives, and there's multi-objective genetic algorithms. So you're going to say, not only do I want to be there in, you know, the fastest, but I'm willing to trade off if I can save gas, if I can save fuel costs. So you might come up with a merit function that has to do with total cost of the problem. It's time, it's money, it's the cost of the driver, and all these kinds of things. Or maybe, you know, I have a whole bunch of drivers and they all have different schedules and they're trying to do different things. Or I have, you know, I want to put as many boxes as I can in the truck. And then, do, you know, all those types of things. So you can apply that to a lot of different DoD problems, and you'll see. So the other thing is, how big do I make my population size? I mean, obviously, bigger is better, but it's not always, And I found that somewhere between 10 and 20 times the size of your genome is really probably a good place to start. In most algorithms, I start at 15 and I tweak it from there. And then, of course, stopping when the best solution stops improving. I mean, that's one way to do it. You just look at every time you go through, you say, look at the best solution. Am I getting better? Am I getting better? Oh, I stopped. I plateaued out. Or you can look at the overall rate of the entire population. Say, is the whole population getting better? Even though my best solution didn't get better, is the whole population kind of getting better? That's another way to do it. Make sense? Okay. I'm going through this pretty fast. This is my last slide, and it looks like the font's got a little screwed up there. But here's a couple of, the first 3 projects are things that I've worked on for the DoD. The first one is called Tempo. It's tactical EW, machine learning, planning optimization. It's a lot of words. Basically what that is you have electronic warfare devices. You want to deploy them in the most efficient way in order to you know, make sure you're either jamming as much of the links that are out there as possible, or you want to be able to hear as many of the enemy units or geolocate them. So how do you do that? Well, it gets really complicated because not only do you have a lot of different targets that you have to prosecute, you also have maybe 3 or 4 or maybe up to 10 jammers. So where do I put my jammers? How do I configure them? You know, which ones have which power? Which ones have higher antennas? Which ones, or, you know, based on your inventory. And I want to use the least amount of jammers possible. I don't want to put people in harm's way if I don't have to. All those types of things. So this program has been studying that for about 6 years now. And we have a pretty good algorithm in place that also provides a lot of visualization. It's really nice. And, you know, it lets you do it manually. So you can go in and say, well, I think I know where to put everything. I can go put it out there. Tells you what the solution is. And then you can have the algorithm do it. And I've never been able to beat it. I've tried many times, but it always beats me. Another application of genetic algorithms is space sensor collection request scheduling. So imagine you have thousands of satellites, LEO satellites that are moving, and they all have different capabilities. And now you have all these collection requests. You want to be able to take a picture from one. You want to be able to do some RF sensing from another. And you have thousands and thousands of these requests that you want to allocate to these satellites. It's another problem that, it makes the traveling salesman problem look like a toy problem. So we've used the genetic algorithm to do that one. And what we did there is we used scaled on the cloud. So now what we do is we have multiple instances of the algorithm running simultaneously, coordinating with each other so that you can scale that algorithm to thousands and thousands of satellites and requests. Really good application is weapon target assignment. That's another place where you have many targets. They could be flying, they could be on the ground, and then you have an inventory of different weapons that you want to use. And those weapons each have a cost associated with them. You don't want to use a nuclear bomb to take out the local drugstore, but you want to be able to use the right weapon for the right target, and you want to be able to do that in a timely fashion. So what we did there is we have two genetic algorithms that run side by side. One that kind of looks at what's called saturation. It says, I want to make sure I don't use all my weapons. I'll maybe take some casualties to make sure I don't use all my weapons so I can make sure I can take care of the real important ones that I know are coming. And then you have another smaller one that actually does the assignments kind of in real time. And did those side by side, and that worked quite well. That little graphic there kind of just shows you the targets and the weapons. The weapons have the arrows coming out of them. You got to make sure they're pointed in the right direction, so the radar will be able to continue to track all those types of things. So there's a lot of considerations. You can imagine the genomes on these things get quite large because there's got to be a spot for every target, for every weapon, and antenna direction, all those types of things. And the last one I pulled from a NASA website. They used the genetic algorithm to design this little crazy antenna. So basically they had this wire, and it represents the antenna, and they used the genetic algorithm to optimize the design of that antenna. And they decide how long each segment should be, where it should be bent, and no human would have ever designed an antenna that looked like that, right? And that turned out to be have the best radiation pattern for that particular application. Well, I think that's it. Yeah, that's all I have. I got through that. Go ahead. Yes.
How, do you have like provisions built in to try to make sure you don't get caught in like a bottleneck?
Well, that's the beauty of the genetic algorithm. So if you use a gradient descent algorithm, you're always going to have that problem. You're always going to be going down to the bottom of the hill. With genetic algorithm, you're basically randomizing your initial solutions all over the solution space. So you're starting in some valleys, you're starting on some hills, you're starting all over the place in this multidimensional space. And so it's similar to a simulated annealing algorithm that does the same basic thing. You can look that. I did put some references in the things. You can look on things, but yeah. And what you can also do is, let's say you get to the point you can run the thing multiple times. It starts to not improve. You can introduce some new random solutions and keep going. And mutate. You can change the mutation algorithm, things like that. So there's really a lot of things you can do. The hard part, though, is to take all that after you've gone through all that and put it into production. Put it into something that is going to be repeatable and do it over and over. Because what you end up with a genetic algorithm is not one solution. You end up with a population of solutions ranked. And it's kind of nice for electronic warfare application because they're all different courses of action. So when you get done, you can say the top 5, maybe where it decided to put it, it's just infeasible because you weren't considering a parameter in the algorithm, such as, it just takes too long to get there, or whatever it could be. So you say, hey, maybe option 3, you can visualize those. Maybe option 3 is really, it's not optimal. None of them are really optimal. They're as best as we can do given the computing resources. And then so you can at least have some options at that point. Good question. Anything else? Another one. Sure. Well, you cannot prove that a genetic algorithm will ever give you an quote-unquote optimal answer, the absolute best. There's been papers written on proving that you can't get the optimal. You know, it might get lucky and get the optimal, but you can't prove that it will. But time complexity is difficult with an iterative algorithm, obviously. If you look at, it's really the population size, which is n, right? It's got to be at least n squared, if not greater. You know, it would depend on how you do that, but I would think it would be at least n squared. Oh, absolutely. All these problems are NP hard problems. Yeah, I should have said that initially, actually. Yes?
Yeah, can this type of algorithm be accelerated by GPUs, etc.?
The merit function is probably your best place for that. After you've got all your evaluations, if your merit function is normally based on some model of the real world, right? So you're able to use a GPU to, and I have, to make sure that that merit function runs as quick as possible. But you have to get all those solutions back into one spot, even if you use multiple processors and bring them all back. You got to bring them back and you got to do that evaluation. And there's a little bit of work, but you can speed it up tremendously. And we've done that actually with AWS and done a cloud application of the satellite project with that. Thank you. Is that it?
Yes, sir.
Okay.
Thank you very much.
Thank you.
Appreciate it.
Very welcome.
This morning before we break for lunch, and then we've got one more session in the afternoon after lunch. Thank you, Joe. It's my honor to introduce Colonel Cade Sy. He's the Chief Data Officer for the Army Network Cross-Functional Team. Colonel Sy started his career as a platoon leader in the 82nd Airborne and then a company commander at the 1st Armored Division. And then somehow he transitioned into being the chief data scientist for Army's Cyber Command, the chief data officer and director of data and decision sciences for Army Futures Command, and then into his current role as the chief data officer for the network cross-functional team. So it sure looks to me like Colonel Sy is the true definition of a data warrior, and we're honored to have you, sir. Thank you very much.
All right, thank you very much. Is this working okay? Okay, all right. So I'm happy to be here. Happy to represent Major General Ray and the network cross-functional team. And not so happy to be between you and lunch, but hey, that's the way things go sometimes. Today's topic is increasing data, Army data centricity, and things like that will help us enable AI machine learning at the edge. So why is this important? So the Army the network cross-functional team has the mission to get the Army ready by 2030 and 2040. So what we're looking at in 2030 is to get ready across different echelons, such as the division echelon, and get our network ready for that, and then transform into an Army network of the future by 2040. And why is this important? So it's the Secretary of the Army's second objective, a data-centric Army. This is going to enable a couple different things. So the Army doesn't necessarily have a problem with getting data. It has a problem that it has lots of data. So what we want to be able to do is embrace certain technologies and enable our commanders to have the ability to make the decision that they need to make at the right time with the right information at the point of the edge. So as we look at data, like I said, we don't necessarily have a problem with having data or collecting data because we do have a lot of it. A lot of it is just trying to process it, clean it, and make it ready for AI and ML at the edge. So previously, we looked at data in different mission areas, and we would put this type of data in bin B, and this type of data in bin A, and this one in bin C, and then we wouldn't be able to go across them very well. So over the past couple of years, we have worked to break down a lot of these different silos and then share data through a set of common data standards. Notably, over the past couple of years, the Army has started along this digital transformation, and we've seen things like the Army Cloud Plan, the Army Modernization Plan, and our Digital Transformation Plan. So this talks about how the Army is going to start to maximize the use of data and enable AI and machine learning at the edge. So as I mentioned, the Army Network Cross-Functional Team, our job is to design the future network. So our objective state of the future network is built upon 4 different pillars. All of them are listed right here, and I'll talk a little bit about each one as we go along. So transport agnostic networking. We want a resilient network which can send information across multiple different paths. So this could be commercial, military, LEO, MEO, SATCOM, any type of commercial type network. We're talking tactical 5G or commercial 5G or whatever we have in the future. But the point is that we can send this information across these different networks. And we're going to do this a little bit differently. So previously, the Army was network-centric. So what does that mean? We focus on the network itself, and we secure the transport. We're worried about securing the system, the path to the other system, and then the other system itself. Now we want to be data-centric. We want to focus on the data itself. So we're going to worry about securing the data. We want to be able to use all of the data that we have and not have to transform it 1,000,000 different times so that it can talk to one system or another system. But we want to develop our systems of the future so that we secure the data, we can transmit the data, and it stays in its natural format, and that our applications then access that data at the time of need. We look at a couple different things in this case. So Network Cross-Functional Team partnered with PEO C3T has been working data fabric for some time, and I'll talk about that in a minute. But that's one of the key enablers of our data-centric environment. The security architecture, a lot of that goes down into things like ICAM, Zero Trust, and other different multi-level securities. Everybody here, for the most part, I imagine, does some sort of online banking. Everybody has an app on their phone. They open up that app on their phone, and they go to their bank, and they see their information. But when I open up your phone and then I log into it with mine, it goes and shows me my information. It doesn't show me your information. We need to get to the same type of sharing of information when it comes to our mission partners. Right now, we design our network so we have 15 or 16 different cross-domain solutions all over the place. And sure, some of them are necessary at some point in time, but we need to get to an environment where we can share information easier. That way we can have a collaborative command and control across our coalition and our other service partners. The bottom line is that if we secure it correctly, we should be able to share information in a more permissible environment that is still secure with all of our partners. And that will take place, like I said, using ICAM, Zero Trust, and all those different security tools. The last part is SEMA dominance. We want to be able to manage the spectrum in which we operate, and we want to be able to secure our network and secure our data. But we also want to be able to have the same type of cyber and EW effects to prevent our adversaries from being able to access their data as well too. All right, there we go. So I told you we're going to talk a little bit about data fabric. So what is data fabric? Well, it's not the end-all be-all solution to everything. It's not going to take all of your data and put it into one environment and lock it all down. It's going to leverage a whole bunch of different things. It's going to help you discover, understand, and then exchange data with your different partners. And a lot of this is built off of experience. So PEO C3T has the lead for this, and they've been working exclusively with Army Cyber Command and our different S&T partners to develop the solution that we're currently using. We've been using it for about a year now. It's been part of PC22, and it's ongoing with experimentation in the Pacific right now. So at PC22, it enabled us to get a little bit away from that swivel chair type of methodology. It wasn't 100% perfect, but it was a step in the right direction, and it helped us see all the different types of sensors and data that was coming out of those different sensors. And it brought this information from the tactical edge up to the enterprise and vice versa. So we've used these technologies in certain events like PC22. It was part of UserPAC's participation in PC22 and ended up staying behind there. So as we test out these technologies, we're also leaving them behind so that we're not testing, giving them something to work with, and then taking away, and then they go back to the old way. So UserPAC has been using this technology ever since PC22, and it's a large part of the exercises that they've got going on right now in Bala-Catan, and then upcoming in Talisman Sabre. So this is a key enabler to them being able to doing distributed command and control. So if you look at the area of the Pacific, it's a massive area, mostly water. And there's these little island chains all over the place, and UserPAC needs to know how it can command and control all of its forces, which are in multiple different places, all the way from Alaska all the way down to, let's say, Australia. So how do they do command and control of all those different entities and be able to share information and a common operating picture across that? So the data fabric, in conjunction with the command post compute environment, tie that all together so that they have that tactical data, the enterprise data, and bring it all together. So bringing it all together like this, like I said, it is in helping to enable AI machine learning at the edge. So right now, through our experimentation portfolio, I guess we'll call it, our campaign of learning as we go across different things between different organizations, all the way up into Capstone for next year, will focus on integrating that tactical data fabric, getting our mission, our command post compute environment updates across all of our formations, and focusing it on a division as a unit of action. But also, we've been working on our own internal development of applications to enable both the command intelligence picture and the common operating picture, the integration of those two, our logistics common operating picture, and how we do tactical fires. We're having internal developers from the Army Software Factory, from the Army Artificial Intelligence Integration Center. Those developers are working and developing in the environment, which is going to be in place for our tactical formations. So they are working on the tactical data fabric, developing and then deploying directly to that, and then it is enabling it to be observed and integrated with the Mission Command Information System as part of, sorry, it's a mouthful, CPCE. Lastly, so how does industry get involved here? So upcoming pretty soon, we're going to have the technical exchange meeting in Philadelphia, and I don't remember the exact date, so we'll look it up. There you go, 24, 25 in Philadelphia. And so this is an even number 10, which means there is 6-4 funding that goes along with it. I believe there are 3 topics that PEO C3T is supporting, but then there are other number, so you got CRADAs and then NetMatix and stuff like that. But what I do want to bring up is that we are currently integrating technologies from our other even number 10s. So as different organizations look to submit their proposals and their RFIs, or information papers based on the RFIs, we do have success stories from this. We're looking at a combat power projection, which is going to be implemented in CPCE pretty soon. And then there's another program with the soldier CFT that is making use of different AI ML technologies looking at how their vast number of sensors can be presented to a soldier through systems such as like IVAS. So there are numerous different ways to do it, but I did want to point out that we have had a couple different areas where the TEM proposals have actually implemented AI and ML solutions into our current compute environment. And this works with our S&T community as well, primarily C5 ISR Center here at Aberdeen Proving Ground. And that is my final slide, and I am open to questions.
Sir, did you say April 24th and 25th or May?
I may have said April, but I meant May for sure. I'm sorry? So it's a network technical exchange meeting, X with 10. Yes?
Sir, Lieutenant Colonel Brian Northup from APEC. So I'm an Intel professional by trade, but I do cybersecurity evaluation. On your zero trust piece, one of the struggles we've had in evaluating cybersecurity has been, although zero trust looks good on every senior leader cybersecurity slide, in practicality from a test evaluation perspective, it's extremely difficult to execute. As you know, layers of bureaucracy, Title 10 versus Title 50, IC authorities, whether it's an AO at the Army level, an AO at a three-letter agency. Take Titan, for example, it's on 4 different enclaves, all on different networks that are different AOs. How do you, I'm interested in you or your command's sort of vision on how we can actually get after zero trust in an operational environment on these new systems that will help the vendor from start to finish be able to incorporate zero trust cybersecurity testing across these enclaves that are highly controlled.
Sure. So I don't have the A to Z answer on that one, but we have been working with Army Cyber and NSA to look at how we can actually implement this in a tactical formation right now. And much like you said, the tactical formation spreads across, so it goes all the way from secure, unclassified, all the way up to top secret, depending on what you're doing. So we do recognize that there are areas of concern right there. But as we've gone through a lot of the different exercises, I think we've been able to learn from this and bring it forward into the next one. And so it's clear to me that what we also have to do is work on bringing it into the test and evaluation piece as well too, because we're never going to get anything approved unless it goes through a successful test and evaluation. So I think that's probably one of the takeaways I'll have to look at here is how do we bring the two together? Because we spent some time doing the experimentation and it's continued to build, but we do got to get it to the point where we can get other communities up to speed so that we can actually certify these products to go through. So we have been working close with DASA DES. It will be an integral part of it. We're trying to look at how the two are going to come together, because we don't want to completely abandon everything that we've done in the past, but we do recognize that if a new reference architecture comes out, we have to figure out how to tie the two together so that it supports it. Because a lot of this, like I said, is crossing from the tactical to the enterprise domain, and there's going to be some bumps and bruises as we go through that. But it is in line with UDRA. We just need to make sure that we stay that way, because even that right now is still being redefined as over time. You know, with initial implementation coming out, I think in the fall to start testing in. So we'll have to make sure that we remain in line with that. All right. Thank you.
Okay, so we're going to break for lunch. Lunch is across the street in the expo area. I encourage everybody to take advantage of it. We have plenty of food. Spend some time with the various exhibitors if you haven't already. And then we have one more session after lunch. We'll regroup about 12:45. And in the meantime, enjoy the nice day, enjoy lunch. Thank you. Okay, we're going to presentation here. I appreciate everybody coming over after lunch. You may have noticed from the original agenda that we Deloitte has very kindly offered to step in and talk about optical AI, digital twins to enhance autonomous operations. I want to introduce Mark Patrick, managing director, and you got to cut him a little bit of slack because he's doing this on very short notice. I have no doubt that it's going to be very informative.
Thank you, Joe. Hopefully this mic is working. Everyone hear me at the sides okay? Fantastic, thank you. Well, yes, thank you, Joe. My name is, Joe said, is Mark Patrick. I'm a managing director in our Deloitte government practice. My particular focus is AI and within that, computer vision. And I lead our computer vision discipline within Deloitte. I've had the fortune over the years to help assist different clients within DoD and across federal law enforcement and helping secure our border with different computer vision challenges, and also assist many of our Five Eyes partners as well, all of whom have similar wonky accents to mine. But this is the accent you get if you live in DC, honest. What I want to do, rather than make this a sales pitch, and then I put up a sales pitchy slide, right? But I promise you, or I'll try and make this the only one today. What I want to do is really explore a specific capability and one example, one demonstration we performed to DITRA, but put that in the context of wider challenges that you may be facing when you're putting together your own AI programs and your own solutions. But Deloitte is able to draw from our quite wide and diverse range of AI skills that we bring to bear on many of these projects. So you may be a little surprised to hear we have over 1,500 professionals in the US alone, many of those cleared, ready to work on these challenges. But the skill sets that we bring are quite diverse. So they do include the normal skills you'd expect, like software architects and modeling engineers and data engineers. But they also include other skills that you may want to consider looking at these tool sets or capabilities yourself, like bringing in ethicists, for example, in making sure that we are building ethical AI capability. So it's really interesting when you apply many of these or apply ways of fixing many of the challenges that you're looking at. When we're dealing with something so new and sometimes so ethereal as AI, we can have some quite unintended consequences to the systems that we build. So I'm really considering what is the impact of the systems that we're bringing, and particularly how explainable and how justifiable are their decisions is going to be really, really important. But I said I wouldn't pitch Deloitte too much, so I'm going to move on to a specific project. I'm not going to pitch and I can't use my technology. There we go. Okay, everything that you're going to see today has been cleared from this demonstration with DITRA. So that this is there's nothing particularly secret in here, but I do think there's some quite special applications of technology that you're going to see. So what we're sort of highlighting here, and what I want to highlight through this is some new trends in AI development and deployment, and some things that you may consider. I'm hoping that when you see the quite vast array of different technologies that are in play here, that you'll see something that you may use. This particular scenario was to rapidly identify different chemical or biological threats within a particular theater area and provide some clear recommendations on how to deal with those threats. And we, as I said, brought quite a lot of different capabilities to bear here. And the things that I want to bring out here are these kind of quite diverse. They don't always go together. Different systems that we brought. So firstly, digital twins. We're going to focus on that and some interesting ways of starting to think of digital twins in the future. Many of you will have used these for training simulations. We're actually using this much more for operational readiness of an AI. And I don't know if anybody's been keeping count of how many times Gen AI and Chat GPT has been mentioned today in the room, but I'm hoping to show you a really positive way of using generative AI for assisting in AI model development as well as we work through this. We're going to see quite a lot of application and decision making about where do you actually decide to put your AI processing, because it isn't always straightforward. There's quite a lot of flexibility about where it goes, but there are some specific considerations that will drive that. And also, I think that we need to move away when we're talking about what's now an overloaded warfighter and an overloaded analyst. We need to start presenting recommendations, not just raw sensor data, or not just a position, a vector, a threat code. So you'll see some application of more natural language ways of showing information here. And then many of the UAS systems, UGV systems as well, that you may have interacted with tend to be fantastic when you're working in a nice communications environment, one that stays nice and consistent through the execution of the pilot or of a mission. But I haven't seen that in the real world as often as we would like. So designing systems to operate in a contested or a denied comms environment is critical, just the same as we train our own people to be able to continue to operate when that communication has been cut. And that's quite hard for an AI to do, and takes us beyond the just application of a straightforward open source algorithm. And then finally, you're going to see some immersive command and control. So placing the operator of the system right in the action, even if that action information is being fed by a UAS platform. Definitely not going to drain this slide. There's too much information on this one, and you're going to see this come to life over this presentation. But firstly, Deloitte doesn't build drones, so we won't provide you a drone with a Deloitte name on it, but we will provide technology to sit on various drone and UAS platforms. Our mission is to make those drones much more effective in the real world. And we've built here a flexible platform that includes edge-based processing, and these techniques that are performed with many different capabilities. You will have seen similar ones, but I hope that you're going to see something quite unique here. We've kind of designed the overall architecture to support so many different mission types. So you'll see here, obviously looking for specific threats within this area, but we'll also talk about things like analyzing infrastructure to see if there's defects within that infrastructure. And if we got time, I'd love to explore a little bit about reacting to drone swarms and things like that using this kind of technology. And it doesn't have to just carry our own AI models either. And Bharat brought that up this morning when we explored Project Linchpin, where a key requirement is to allow for replaceable AI, which brings many specific requirements on vendors and providers of tools to be able to slot in capability and know that it's going to perform at least as well and ideally obviously better than the AI that it replaces. But our job here and with this system is to augment human performance. So fundamentally provide a tool that can do something faster and more accurate than a non-AI assisted system. And in one example of using this system, we were able to jump up our performance of inspecting infrastructure and defects within the infrastructure to an accuracy level of 93 to 99% from a human-based accuracy of 80%. But I think the real key benefit there was we were able to do that in about a tenth of the time. So the time factor and not needing to have experts in the area is really, really key. So I want to compare here the difference between kind of old process and new process and where AI could really help here. So if you think about what we're doing, we're bringing a UAS to an area, number of buildings within that area, normally advanced mission prep effectively is going on. And typically, the way that we have used digital twinning to accelerate our process, we'd have taken maybe 2 to 3 days. We'd have done a site survey in advance, we'd have come to a site, we'd have mapped that site out, we'd have done a number of manual flybys around a site in order to understand what are the waypoints, what are the different elements that one might want to inspect in advance. But that isn't always a realistic set of mission parameters, right? We don't always have a few days to plan. Often we do. Sometimes we have weeks. But things even change on a daily basis. So even fantastic planning that's performed for a mission over a period of weeks or months, you'll find that you deal with something new when you get to on the ground. And what's happening during this prep activity is huge amounts of data are being collected. And again, as we learned this morning from Linchpin, that problem is not going away. We're going to see ever-increasing amounts of sensor data come through, and certainly is overwhelming already our analysts and our teams to make sense of that. So what we wanted to do is show that prep cycle that would normally take 2 to 3 days could be shortened to hours, and use digital twins of the environment to assist in that. And we can create those digital twins in a number of different ways. So one of those ways is to, if we can't visit the site beforehand, is to work from geo imagery or any other collected images from that area, even down to architectural drawings, and do a pre-model, like a kind of preconceived model before we get to site. And ideally then augment that with a autonomous flyby through the area based upon that basic model that we have created. So if, for example, we are looking at, do we want to perform an inspection of, say, a remote embassy overseas where we don't have time to do a massive site visit beforehand, then we would create that twin in advance from either public or privately sourced information. But we can also create that information directly from flybys. So instead of this whole cycle of multiple days, we're ready within minutes or hours to understand what's happening within the environment. We'll talk a little bit more about onboard compute, so I don't want to push on that too much right now because I think there's some important considerations to talk about. But then obviously we're applying a certain mission parameter set on board that AI and then presenting those results back. So all of this really cut the setup time down from days to a few hours. 1 minute video. I don't think we'll have sound for this, though the sound is pretty cool. So what's happening here during the DITRA exercise is the drone is identifying a number of different threats overlaid within a GeoInt mapping, set of mapping tiles. It's providing that viewpoint from what the drone or multiple drones can see directly to a HoloLens-equipped local command who's able to, in this case, create both verbal commands for other team members to be able to respond, but also interact directly with the system to direct the drone in order to get further information, but also to receive a direct insight from what's going on rather. So over here is this type of chemical, it's spreading in this area, there's a wind direction coming in from this side, all those extra bits of information that we are able to gather. So I mentioned about many of you will have used digital twins probably for running training simulations for humans. And that's probably been fairly common over the last couple of years. we have seen tremendous value over the last 18 months or so in using a digital twin to train an AI. So we talked this morning about the need for a lot of training data for models and the massive amount of setup time that it can take to get that data right and the labeling right. But what we want to do here is use digital twins to allow the AI that would be running on the drone. So we basically connect the drone to be fed sensor information into its sensors from the virtual environment. So we're trying to make this look as real as possible to the drone and allow that drone to perform its missions based inside the synthetic environment first in order to run different mission parameters and see how effective the AI is actually performing. And one of the great benefits about that is it allows us to rapidly optimize that AI at much faster than real time. So typically, in order to see how an AI system running on a drone will perform in the real world, maybe you can do 2 experiments a day or something like that. We're able to perform tens or hundreds of experiments per hour by running within a simulated environment. And I think one of the further real innovations that we've been able to see through Gen AI, in the same way that if there are many gamers in the room, you'll probably be used to games where an AI will populate a very realistic environment from just a small number of parameters. We're able to start to create these quite diverse environments by giving fairly simple instructions to generative AI, but bringing in very realistic photo level textures and other environment cues for the AI to spot and learn from. Which obviously needs to be reasonably realistic to the real world, but those that are quite used to human vision in here will know that actually one of the first jobs of computer vision AI is to simplify the scene as much as possible. So it's quite interesting. You don't necessarily need the level of resolution that you might need in data for other challenges. The autopilot thing I think is really interesting. So, as I mentioned earlier, normally what will happen when you set up a drone-based system for inspecting an area is you'll give it a set of waypoints, and for safety, if comms are removed, then that drone will normally hover and it will normally land. What we wanted is a much more flexible way of thinking about, well, what is the mission that this drone is meant to perform, which is much less about the waypoints that it's going to fly, although those are important in order just to generally know the environment, know what it's covering, the whole area. But it's being given very specific mission parameters about what is it actually looking for. So in this case, it has an 8 chemical sensor system on board. So it's looking for different types of chemical plumes within the environment, but it could be looking for many other things. So we broadly want that to continue to fly its mission when that comms is removed, and then to send the payload of insight that it's generated when that comms is brought back. And sometimes we're deliberately keeping, and you'll need to deliberately keep the comms payload very low, either because the environment is contested, and therefore your bandwidth may well be reduced, or you want to kind of keep the signature level very low. Because if you're sending some of this data raw, you've got a lot of sensor data that's moving around the environment. And that's one of the key things about deciding as well where you're going to place the AI processing. Because if I was going to, and I don't have any tattoos, but if I did, I'd probably start with swap, because it's the thing that I think about quite a lot. So size, weight, and power. And that's one of the major things that drives your own decisions about where you're going to put processing on board anything that's going to carry batteries, right? I think weight is becoming a solvable problem now. In this particular case, the payload that we're delivering on this UAS platform is around about a pound. We could bring that down if we had different environmental hardening, and we're seeing much lighter payloads available, depending on the processing requirement. We wanted to keep a reasonable amount of spare model hosting environment to be able to put third-party models on this system. But these are quite power-hungry systems. I think we've seen through NVIDIA and others, but particularly NVIDIA, a massive reduction in the amount of power that's required to drive these systems over the last few years. So things that you felt maybe weren't possible for onboard processing 2 years ago, I think you'll find are much more capable platforms now because of both the sheer compute power, but also the reduction in battery size. Other things that you'll need to be thinking about is where are you getting the best view of the sensor data? If you've got unlimited bandwidth, then you can do your processing on a ground link if you can push that data down. If you don't think there's a major consideration about a contested or denied comms environment, because obviously that data will be normally encrypted, but you can probably break it. But why use all that data even if it's available? Because right now we often think about just one drone system or 2 drone systems within a particular area. But we're certainly working out how we defeat swarms of UASs coming at our facilities, and we will no doubt be using the same technology or preparing it for use against our adversaries. So even if we think we have enough bandwidth in an area for 1, 2, or 5 UASs, we have to start thinking about 100, 500 UASs at any one time. We need to create platforms that can carry different AI and allow that AI to be loaded very quickly. And then when that AI is responding back, we need to be able to interpret that very quickly and in a way that requires the minimal training to the operator of the system. And one of those ways of achieving that is to move to a natural language way of presenting information and automatically generating that language segment from a more compact sensor kind of response. So I think it's really key that we give and we send the normal kind of cursor on target information, but think about how we can enrich that very quickly to allow the person receiving the information to make a specific decision, and how can we join that together with other information that they may see through systems that can place that more in the mindset of the person that's consuming the information. So at all times, kind of, we want to, and I'm sure you want to reduce the overload on the person receiving the information. We are nearing the end of my slides, I promise. This was the fun bit, was using, I'm sure many of you have used HoloLens capability within this room, and other similar VR capability as well. But working out how we could build a system that very quickly allowed somebody new that's interacting with the capability to have a kind of sandbox C2 system and be able to pull and interact with that system and do that intuitively was where the real craft came in designing this system. And we were very fortunate that we were working with a client set there that were able to pick up that capability immensely quickly, and within typically 10 minutes or so were quite expert in interacting. But a key thing really was, how did we use cues around natural language and other things to be able to draw the eye of the user very quickly to the areas of interest, rather than them having to kind of scan through multiple screens. We've applied this capability to lots and lots of different mission types. I mentioned swarms. I'm not going to have enough time to talk about them as much as I'd like, but for me, when I've pulled the thread of where we started with this capability, which was intelligent inspection, so how do I know if there is a feature of this building, like a tower on the top of the roof, that's in imminent danger of collapsing, and to be able to do that on a regular basis without human inspection. and then pull the threads to be able to look at advanced change detection within a scene. And I'm particularly interested in what happens after an event. So we, for example, are looking at, many people probably in this room as well, how do we deploy systems to counter a UAS attack, where that attack may be using large numbers as well to overwhelm our ability to deter it. Being able to use autonomous systems, which aren't kind of a one-to-one to an analyst, to be able to survey a scene before and then to perform that surveillance of the whole area afterwards, to go, well, what's different? What's been placed on the top of that tower? Is it an adversary sensor? Is it a drone waiting to take off again that is just sitting nice and quiet? That kind of advanced scene detection capability, I think, is going to be really key for us over the coming years to prep for this type of attack. So it's really important that these systems are platforms that other algorithms and other capabilities can sit within. So this is my last slide. Just some things to take away. You know, from a Gen AI side, very exciting to talk about writing reports, and I'd love to be able to write all of my proposals or have them written for me in the background. I do worry about them all like going to the lowest common denominator, of course. But how can we use Gen AI and other capabilities in synthetic data creation in a really interesting way to speed up our training process? And then how do we make sure that those are applicable to the real world, so we don't overfit our models to synthetic data and then find, well, they work well with that, but not outside. Think about how any of the AI that you're deploying is going to work when comms are taken away, and test that you're designing systems and designing platforms and capability that are resilient to that in the same way that we train our warfighters to be able to make those decisions on the ground on their own in the absence of extended communications. How do we reduce the amount of information that we are sending to the pinpoint interesting and important pieces of information, but then be able to expand that out with a secondary question that says, well, why are you presenting this to me? A system that allows the consumer of the information to see then the bigger picture based upon a secondary question. And how do we reduce the mission prep time? How do we use technologies like this and other AI technologies to prepare either our AI or our people for the environment that they're about to jump into, so that they can react more quickly and react quickly to changes that our advanced prep didn't allow us to see. So that's kind of the end. I'm happy to take questions if there's a few minutes. Yes, sir. Yeah, so we weren't using any kind of novel new sensor type in here that was bringing a different kind of, if you like, percentage accuracy than kind of the best-in-class sensors that are out there. The things that we were able to do were be able to autonomously keep the sensor away from the direction of the bloom, for example, because as you know, if that gets too close, you overload it, and then you... Oh. Yeah. Got it. Yeah. So we will basically take in a commercial off the shelf or a specifically government developed sensor, and then take in parameters like stay this far away from the bloom, take into account a wind effect, things like that. Yes, sir. Yeah, so we haven't explored the kinetic side ourselves, but I definitely understand that the requirement there, and also the requirement for that to still operate in a GPS-denied environment as well. And one of the things there is the cues that the AI can take from the scene certainly help in the latter very well, so that allows it to continue to move to its next mission point without necessarily those GPS comms, because you've got scene detection and change detection. Yes, sir. We've done, we haven't, so we've done UGV, but I don't think I've seen an application for say a water or underwater vessel or others. Clearly there's some considerations about what can the sensor see and whether you then have to move to different sensor types to operate in those areas. But we'll operate there without a normal EO sensor, for example. Yes, sir. Oh, sorry. Unless any of my colleagues say otherwise, I don't think we have experimented with 3D payloads, or 3D printed ones, sorry. I haven't seen it enough. But I'm happy to follow up if after this, if there's a specific sort of application we could explore. Got it. Yeah. And there's certainly, I know, a lot of need for being able to deploy a payload autonomously into different areas, often large numbers of sensors to be able to cover a fixed place and maybe retrieve them later. That's obviously more of a challenge. I think that's it, Joe. Thank you very much for your time, especially after lunch. Thank you.
Very informative. You're jumping in for us here. I want to thank you for staying for the entirety of our industry day here. Very much appreciated. A lot of people have asked about slides, so you will be getting an email with a link to we'll have all the slides posted, so you will be able to download them. I think you have contact information for are still here across the street for about another half hour. Across the street. But we want to thank you very much. Discussions have been great.